In the workshop, Michael Kapralov will tell us about data streams.
Okay, thanks for the introduction. I will talk about algorithms for processing massive data streams, and in general, these two talks will be organized as follows. I will start with some basic classical techniques for approximating statistical properties of large streams of data sets, large streams of data items, and once we develop these techniques, I will show some of the more recent applications to processing massive graphs in dynamic streams. So specifically, I will talk about connectivity and related questions in the first part, and I will show how to construct spectral approximations to graphs in dynamic streams through sketching in the second part of this talk. Okay, and do please stop me with any questions. All right, so this is about the streaming model of computation. What is the streaming model of computation? It's a model for processing massive data sets, and in this model, we think of the algorithm as observing a very long stream of data items. So these data items could be a lot of things. For example, IP packets, tweets, search queries, and whatnot. Well, the classical streaming question is the following. As our algorithm is scanning this very long stream of data items, it is limited in its space usage, so it can't store the entire stream. It has to maintain a small amount of bits representation of the stream at all times, and at any point we should be able to stop this algorithm and query some basic statistics of the data stream. Some basic statistics include things like the number of distinct elements that we have seen so far, or something about the distribution of frequencies of the data items, for instance. Okay, well, this was the classical motivation for the streaming model, and more recently, the question of processing massive graphs in the data streaming model has received a lot of attention. So these days, we care about more complicated statistics of data streams. So here, think of this very long stream of data items, let's say being a very long stream of edges of a graph. And what we want is to be able to process such streams where the edges perhaps arrive and possibly depart. And at the same time, at every point in time, we want to be able to stop our algorithm and ask it about basic graph parameters for the graph that we have received so far. For instance, perhaps approximate the cut structure of the graph, spectral structure of the graph, something about the shortest path metric, matching size, vertex cover, and other questions. Okay, good. So in this talk, I will first explain some of the basics of how do you solve problems from class 1, and then talk about graph analysis. So I'll start with the basic stream statistics, and specifically I will remind you how classical sketching algorithms such as distinct elements, AMS sketch, and L0 samplers work, and at the same time I'll tell you about some of the recent results on those as well. Okay, so what is the distinct elements problem? It is probably the most basic streaming algorithm. Here our algorithm is given a single pass over a collection of data items, I1, I2 through I something. These data items, think of them as, let's say, integers between 1 and n. And let's assume that we know n. The size of the stream is poly-n bounded. And what we want is to scan the stream. And at the end of the day, we want to be able to know how many distinct elements we have seen so far. And we want to have small storage. So for example, the trivial way of solving this problem is to just store the entire stream, sort of hash the data items. That will be prohibitively expensive. It would take space proportional to the number of these data items. We want space polylogarithmic in the size of the stream. Okay, so here's a pictorial representation. For instance, suppose that our data items come from a universe of size 10. So they're numbers between 1 and 10. And our stream is just a sequence of such numbers. So here they are coming in at the bottom. The sequence is 3, 4, 3, 2, 10, 3, etc. And as the stream is coming in, here on the slide I'm also maintaining the frequency vector representation for that stream. In particular here, what this shows is the number of times every given item appeared. For example, the item 1 appeared twice, item 2 appeared 5 times, etc., etc. Okay, well, as we see, this stream is reasonably long. At the same time, the number of distinct elements here is 8. So our task is to output 8 on a stream like this. Okay, so why do we care about such problems? Well, the classical application is monitoring network statistics. For instance, suppose that we have a router. So here it is pictured on the slide. And this router is a device that has a limited amount of space available. And the router is observing some IP packets that are going through it. If every IP packet goes from some source to some destination, and the IP flows can be encoded by this matrix, where the rows correspond to all the possible source IP addresses and the columns to all the possible destination IP addresses. So as the packets come in, we can think of updating this matrix, similarly to the vector on the previous slide. Okay. At the end of the day, we want to be able to figure out how many distinct source-destination pairs have been engaged in communication through this router. Okay, so of course the router can't store the entire flow, it's too much space, and we want space polylogarithmic in the size of the universe. The size of the universe here is all the possible IP addresses. All right, good. So formally, what would we like to solve? This is our distinct elements problem. Single pass over the stream of data items. Assume that they come from some universe of size n, and the size of this universe is known. What we want is some good multiplicative approximation to the number of distinct elements. Let me denote the number of distinct elements by k. So we want to output some k hat, which is multiplicatively close to k, sandwiched between 1 minus epsilon k and 1 plus epsilon k. And for constant epsilon, we want to have storage only polylogarithmic in n. Okay. We also want success probability, at least 1 minus delta for some parameter delta. Turns out that such algorithms have to be randomized, so we have to tolerate some success probability, as in some failure probability. All right, very nice. So let me remind you how such questions are solved, and this will be a nice way of introducing sketching techniques. So it turns out that it's easier to think about the decision version of this problem. Namely, don't try to approximate the number k of distinct elements, but rather just try to solve the problem of, given a threshold t and a data stream, figure out, have we seen more than t distinct elements or fewer than t distinct elements? That is, we want an algorithm that if the number of distinct elements is bigger than 1 plus epsilon t, says yes. If it's smaller than 1 minus epsilon t, says no. If we have such a thing, we can easily run this algorithm on a sequence of geometric thresholds, and we will be able to get our multiplicative approximation. Just to check when the answers switch from yes to no, and output that number. All right, and this will not really affect our space complexity by much, because it's only a log in the universe size, and some dependence on the precision. Good. Okay, well, how do we solve this problem? So the classical approach to this is as follows. So here's our frequency vector representation of the data stream. And we have a parameter t. We want to know if we have seen more than t distinct elements or fewer than t distinct elements. What we do is this. We select a random set S, subset of the universe, that includes every given element of the universe independently with probability 1 over t. And so here it is, this red set, for instance, for this particular case, it contains the numbers 3 and 6. And now, as the algorithm is scanning the stream, the algorithm will simply maintain one counter. And the counter will be the summation over all elements I in S, this special red set, of xi. So if xi here is the number of times the ith element derived. So basically this is the vector x. Okay. Well, note that, of course, you can't compute this number, but you can maintain it, because as an item arrives, an arrival of an item can be interpreted as a request to increment xi by 1. So this can be easily maintained in the data stream and takes only one word of storage. Good. Well, at the end of the stream, if we observe that the counter is positive, we output yes. If the counter is 0, we output no. And this indeed sounds reasonable, because we wanted to know if the number of distinct elements is bigger than t. When will the counter be positive? Well, it will be positive when the set S intersects the set of distinct elements in the stream. And if S is the size of if the number of distinct elements is large, this random set will probably intersect the distinct elements. So the counter will be positive, and we'll say yes. Otherwise, we say no. All right. Good. So this is our basic decision version. From this decision, from the solution to the decision version for the distinct elements problem, it's quite easy to get the full algorithm. Indeed, this is what we do. We choose a uniformly random subset S and maintain a counter. It is not too hard to verify that indeed, if the number of distinct elements is substantially higher than t, let's say bigger than 1 plus epsilon times t, then the probability that the counter will be 0 at the end of the day is somewhat small. Indeed, what's the probability that the counter is 0? It's the probability that none of the distinct elements make it into our random set. It's 1 minus 1 over t raised to power k. So that's roughly e to the minus k by t. And if k is bigger than 1 plus epsilon times t, then that's a little bit smaller than 1 over e. If k is smaller than 1 minus epsilon times t, this is a little bit bigger than 1 over e. Very nice. So one round of this can give us a little bit of a signal as to how big the number of distinct elements is. In order to boost this into a high confidence algorithm, all that we need to do is just maintain these estimators for uniformly random sets and look at the statistics of the union of these estimators. If more than k by epsilon, so if we maintain a certain number of these estimators, if a large number of them say yes, we say that the number of distinct elements is small. Otherwise, we say that it's big. Okay. Yes.
So are you assuming that the numbers that you see are drawn uniformly at random from the entire set?
Oh, good question. So the question was, are we making this assumption that the numbers that we see are uniformly random? Let me see. Good. You mean the numbers that we're actually observing in the stream?
Yeah.
No, we're not making this assumption. Right. We are not making this assumption. So note that the stream is basically in one-to-one correspondence to this frequency vector x. Okay, there's the ordering as well, but our algorithm maintains counters, so the ordering doesn't really matter. So this result holds for any choice of the data stream. Right? So this is actually exactly the reason why we choose a uniformly random set. Right? So for example, if I knew that the actual identities of the distinct elements were uniformly random, I wouldn't need to choose the random set S here. I could have just chosen a fixed set S, and then the same types of bounds would have held. Any other questions?
I didn't quite catch when you transitioned to the decision version of the problem.
Yes.
You said that you would choose T by doing a search over but it's a streaming algorithm, and you cannot. You assume you can make multiple passes, or?
No, great question. The question was, why is the decision version enough? Okay, so what I said here was that if we have a small space algorithm for solving the decision version, then we can get the multiplicative approximation from this this algorithm. Why? Let's just run a logarithmic number of instances of this algorithm in parallel. Right. Specifically, we choose all the thresholds, a geometric sequence of thresholds between 1 and n that increment by a factor of 1 plus epsilon. At the end of we maintain all of these algorithms. At the end of the day, we ask each and every one of them, well, is the answer more than t? And then we look at the answers that they give. Well, presumably what will happen is that for small t's, they will be saying yes. At some point, they will uniformly switch to no. We just look at the largest threshold for which everything below said yes.
So in the space complexity based on t was what?
Oh, okay, good. So the space complexity does not depend on t. Excellent question. Yes. So note that the space complexity is oblivious to t. The only thing that t controls is, which rate how big of a set S do we take? So if I want to know if the number of distinct elements is bigger than t, I should be looking at the restriction of my stream to a uniformly random subset of size about n by t. So that with some probability, I get a signal basically. Do I have an intersection or do I not? Yes?
Is there a way to get a randomness efficient version of this?
Say again?
Is there a way to limit the number of random coins you need to use?
Oh, yes. Good. Thank you. So here, of course, I said let's choose a uniformly random set S. And as Clement is pointing out, that this looks a little bit expensive because, as stated, if I count the space that I the number of bits that I need to store the actual random set, it's a uniformly random set, so I need omega n bits, for instance, if my threshold is a constant. So that's a problem. However, one can redo the analysis using pseudorandom number generators. Basically, in reality, what we would do is take a pseudorandom set. And there are general purpose techniques that say that, for instance, if you have a space-bounded algorithm that relies on linear sketching, then you can pretty much do the analysis assuming that you have a purely random set, and then invoke a powerful tool, such as, for instance, Nissan pseudorandom number generator, that shows that if your analysis establishes correctness of the algorithm under the assumption of a purely random set, then the algorithm will work with high probability if you, instead of that, feed it a pseudorandom set. And the pseudorandom set can then be generated in small space.
It might be worth mentioning that this S can just be pairwise independent.
Okay, good.
Oh yeah, maybe you're getting
Good. It is also indeed good to mention that this S can almost be pairwise independent. The way I phrased this analysis, it actually cannot be, because sort of in order to say that the probability of the counter being 0 is 1 minus 1 over t to the k, I actually did rely on full independence. However, so in this particular case, you can use a pseudorandom number generator. That's a general purpose tool that says, if your algorithm works assuming perfect randomness and uses a small amount of space, then you can fool it. You can give it cheap randomness and it will work as is. Or equivalently, or related development, you can redo the analysis assuming that S is, the set S is generated using a pairwise independent hash function. The analysis will have to change a little bit because in this case the probability of a counter being 0 is not 1 minus 1 over t to the k. So some space bounds will change a bit, but morally it will all be the same. Okay, very good. Other questions? Good. All right. Very nice. Good. So this is our very simple, one of the classical algorithms in the streaming literature. We sort of first got this estimator, which just intersects the set of distinct elements with a random set, and checks if the intersection is 0 or not. And this can be done using a single counter. And then this only gives you sort of a slight signal, namely the probability of being 0 and non-zero is different when the number of distinct elements is large or small. And then you boost this signal by independent repetition. Just run 1 over epsilon squared times log 1 over delta copies of this algorithm and see how many of the algorithms say yes and say no. Yes?
I'm just curious, the way you worded these, like sort of summing as a counter is, it seems very more general than you're speaking of here. Are you going to, is that hinting ahead or?
Sort of say again?
I'm just curious, I guess like the way I would phrase this is probably, not to intrude on this, but like just saying that like, was something seen or not, but you've said 0 versus greater than 0, is it leading into the next part?
Excellent question. So the question was, why are we summing counters? Because really the only thing that we used was this counter 0, was it non-zero? Yes, and indeed if my stream only contains insertions, if elements only arrive and never depart, I would be able to easily solve, or if instead of using a word of space, I would use a bit of space, and I would equally well solve the problem. And this indeed is hinting towards the next part, and this is really what these two talks are about. The algorithm that we obtained has a very nice property. Namely, it can be seen as, basically what it does is it takes linear measurements of the frequency vector of the data stream. So remember, we have the data stream with items arriving, and one can represent it as a vector x, where the ith coordinate of x is just how many times x arrived so far. Right, so because our algorithm was summing, it was a sum over xi's, in fact, it can be seen as a linear operation. And in particular, this means that if our stream is more general, in particular, some items arrives and sometimes items get to depart, so we delete items from the stream, the algorithm works as is.
What if you allow negative x's? What if you allow negative x's?
Good. It works as is only as long as x is non-negative at the end of the stream. So if x gets to be positive or negative, then this particular thing will not work. Okay, good. So summary. This is a simple example of a linear sketching algorithm for data streams. Our algorithm generates a sketching matrix S. This is a matrix with m rows and n columns. N is the universe size in this case. And if m is some small parameter, for this particular algorithm, it's basically a polylog. And now as the elements of the data stream arrive, our algorithm maintains the matrix vector product S times X, which is denoted by B. And whenever it's asked to provide the answer, it runs some kind of a decoding primitive on this summary here. So note that the number of rows times log m is the space complexity, because we're assuming that all our operations are on poly n bounded integers. Good. Very nice. So what we just did was approximate the number of distinct elements in a stream, which is also known as the L0 norm of the frequency vector x. A natural question to ask, which has been asked in the literature, it's a classical question, is whether or not we can approximate p norms of this frequency vector x for other values of p. And what is the space complexity of approximating such norms? We've noted, for example, that the L infinity norm is the max, sort of the most frequent item, and the L0 norm is the number of distinct elements. Okay. Good. So this is known as the frequency moment question. The pth frequency moment is just the pth norm of the frequency vector x raised to power p. Okay, so question is, how much space is needed for 1 plus epsilon approximation to the pth norm of vector x, let's say for constant epsilon. And it turns out, this very, very nice result, that polylogarithmic space, that is space comparable to what we have just obtained, suffices for all p's between 0 and 2, actually including 0, as we have just seen, but polynomial space is needed whenever p is bigger than 2. So what we just, yes?
Is there any intuition why there's such a sharp shift at p is equal to 2?
Aha. Great. So the question was, is there some intuition behind this sort of phase transition at p equals 2? I guess one version of generating intuition is for all p's between 0 and 2, sort of p-stable distributions exist. Namely, for instance, the Gaussian distribution is 2 stable, right? As in, if you sum up independent Gaussians with some variable x is p-stable, if the sum of alpha I xi is distributed as the pth norm of alpha times x. So for example, the Gaussian distribution is 2 stable, but the p-stable distributions exist for p's smaller than 2, and they do not exist for p's bigger than 2. And I would say that probably reasonable intuition for why they do not exist is the central limit theorem, because sort of for p's greater than 2, you have to have variance, and then sort of you have to converge to the Gaussian, but that's just intuition. Good. Yes?
Are there schemes that achieve the red lower bound?
Yes, there are schemes that roughly achieve with some polylogs. Yes, so all this is achievable. Pretty tight bounds are known for all of these questions. Okay, good. Good. So we just designed an algorithm for one of the extreme cases, namely p equals 0 for p moment, pth moment estimation. Let me remind you, or tell you, how you would approximate the pth moment for the other extreme, namely for p equals 2. So suppose our goal is this. We have a data stream arriving, and we think of x as the frequency vector of this data stream, and we want to approximately compute the L2 norm of this frequency vector. There are good reasons for that. For instance, this is known as Gini's surprise index. You can think of the L2 norm of frequency vector of a data stream is sort of a measure of how skewed the distribution of data items in the stream is. For instance, if you have one outlier then that occurs a lot of times, it will affect the L2 norm heavily. Okay, so good. Suppose that we want to approximate the L2 norm. How do we do that? Well, the classical approach, also known as the AMS sketch for Alon, Matthias, and Szegedy, is to generate uniformly random sign vectors. Let R1 through Rn be IID random variables that are uniformly random signs. So Ri is +1 or -1 independently with probability 1/2. And now as the data items are coming in, the algorithm, or our algorithm, would maintain the following dot product. We'll just maintain the dot product of this random sign vector with the frequency vector of the data stream. So let's call that Z. So this is easy to maintain under increments or decrements of x. It's not hard to verify that this is an unbiased estimator. So if we output z squared, this is going to be an unbiased estimator for the L2 norm squared. And now the actual algorithm simply takes an average of, let's say, log 1 over the failure probability divided by precision squared, independent runs, independent such estimators, and then outputs this average. Now, this is also known as the Johnson-Lindenstrauss transform. I guess the more standard way of phrasing this would be with Gaussians, but for streaming applications, it's easier to deal with ±1 vectors. And furthermore, as before, one doesn't really want, in order to approximate the L2 norm, to assume that these sign vectors are uniformly random. One can get away with bounded independence. It's just 4-wise independence suffices for the purposes of this analysis. And such random variables can be generated cheaply. Okay. Good. So let me summarize. We have just defined a couple of classical algorithms for data stream applications. And specifically 2 algorithms, one for approximating the L0 norm and the other for approximating the L2 norm of a frequency vector of a data stream. And both of them operate in the linear sketching framework. Namely, they generate the random sketching matrix S with a small number of rows, and then maintain, as the increments or decrements, as items arrive or depart in the stream, the matrix vector product S times X. Very good. If I want to approximate the L2 norm of the frequency vector, then my matrix S is basically just a matrix of random ±1s. And the decoding is just take averages, for example, if I have enough independence. If I want to approximate the L0 norm, then what I do is I generate the matrix S to be a matrix of zeros and ones, sampled from sort of at geometric rates. And the decoding then just takes medians. Very nice. So in what follows, I will show how techniques of this type can be used to approximate graph parameters in data streams. In particular, we'll see how techniques similar to L0 norm estimation can lead to space-efficient algorithms for constructing spanning forests of graphs in streams where edges can be both inserted and deleted. And, oh, that's interesting. Okay. In the second part, I will talk about how techniques, or how L2 style techniques let us design algorithms that approximate the spectrum of the graph in data streams when edges get to arrive or depart. Okay, good. All right, so this brings me to graph sketching. And before I go to graph sketching, let me define the basic graph streaming model. So this basic graph streaming model is the following. Now, we think of the algorithm as receiving a stream of data items, but the data items are edges of a graph. So here's our input. It's an undirected graph G, and I will only talk about unweighted graphs. We think of the vertices of the graph as being known. So let's say vertices are numbers 1 through n. There are n vertices and m edges. M could be as large as n squared. Here are the vertices shown as green dots on the slide. Now, the edges of the graph arrive in some arbitrary order in a stream, something like this. And as the algorithm is scanning the stream, it is constrained to use a small amount of space. Oh, all right, so before, when we were talking about approximating basic statistics of frequency vectors in data streams, the small amount of space was polylogarithmic. We were shooting for polylogarithmic space algorithms. Now here in graph streaming, it is customary to assume that the space that the algorithm has available is at least linear in the number of vertices. In particular, we sort of assume the minimum possible, also known as n polylog n. There are good reasons for that, and the reasons are that often, for questions that we want to solve on graph streams, the algorithm does need at least n space to just store the output. For example, imagine trying to compute a spanning tree of a graph. Just output size is n, so you need about n log n to store the output to be able to output it at some point. Or maybe you're trying to compute a large matching in a graph. So the output size, again, could be easily comparable to the number of vertices in the graph. Okay, good. So we're assuming that we have O tilde of n space, so O tilde stands for n polylog n. And ideally, we want single pass algorithms. Take a single pass, output the answer. So this is known as an insertion-only stream. And in insertion-only streams, even such basic questions as connectivity actually turn out to require linear space.
So insertion only means we only add edges?
Yes. So for now, let's think of only adding edges. Good. So let's consider a very simple problem, very simple graph problem on insertion-only streams. I'm getting as input a set of edges of a graph, and I want to construct a spanning tree, or maybe a spanning forest. There is no guarantee that the graph is connected. Well, that's very easy. As the edges come in, I simply maintain a spanning forest. And I will always, the forest will never contain more than n-1 edges, so my space complexity will be n log n. So suppose that, let's say, an edge arrives. If it connects two components, two fresh components, I keep the edge. If an edge arrives and connects two vertices that are in the same component, I don't keep the edge. So this goes on and on. And at the end of the stream, I do get a spanning tree of the graph. Very nice. That is very easy. But suppose now that we still want to construct a spanning tree of the graph, but edges can be both inserted and deleted. And it does happen in networks that change dynamically over time. So is it possible to construct spanning trees of graphs in dynamically changing networks, so this both with edge insertions and deletions, and still do this in the optimal n log n space, or n polylog n space? Well, the problem turns out to be a moment of contemplation reveals that we can no longer get away with a very simple algorithm. Well, suppose that we have this graph here. And if you look at this graph, then this edge is a bridge. And any spanning tree of the graph will definitely have to keep this edge. On the other hand, in a stream with insertions and deletions, the following can easily happen. Well, maybe at some point I receive this graph in the stream. And after that, I receive a lot more edges that cross this particular cut. And my algorithm still needs to maintain some small space summary. So at this point in the stream, when I added a bunch of edges, the red edge that used to be important before does not look important anymore. So if I think of an algorithm that stores n polylog n bits of space, at this point, there is no good reason why it would be interested in this edge. On the other hand, I do get to delete edges. So let me construct a stream where a ton of edges are inserted that go across this cut, and then at some point deleted. So now this is interesting. How can we design an algorithm that still retains information about this red edge, despite the fact that in the middle of the stream, this edge was not important at all? Okay, good. So it's clear that very different algorithms are needed, and that's exactly where sketching comes in. Linear sketching, as we have seen, is a very nice primitive, because if I'm able to design a linear sketching style algorithm for my data stream problem, then this algorithm seamlessly translates to the setting where edges can be both inserted and deleted. And this brings us to graph sketching. So graph sketching is the following idea. This is an idea introduced by Anguche and McGregor in 2012. And the main idea here is to apply classical sketching techniques, such as the ones that we just looked at, namely distinct elements or AMS sketches, on the edge incidence matrix of our input graph. Okay, so here's the input graph pictured on the slide. And let me remind you what the edge incidence matrix is. So here's the edge incidence matrix, we'll denote it by B. It's a matrix with n choose 2 rows, one row for each potential edge in the graph, and n columns. The columns correspond to vertices in the graph. Now, each row in this matrix is a potential edge in my graph G. So for example, if an edge is in the graph, so for instance, here's this orange edge. If the edge is in the graph, an edge UV, then the corresponding row of the edge incidence matrix is nothing but chi u minus chi v. Sort of chi u is the indicator vector, is the coordinate vector in direction u. In other words, for edges that exist, the row contains a 1 at one of the endpoints and a minus 1 at the other. Basically, we think of first orienting the graph, and then the uvth edge of the uvth row of the matrix will contain a minus 1 at u and a plus 1 at v, and the orientation is arbitrary, it doesn't really matter. Okay, now if the edge is not in the graph, then the corresponding row is 0. Okay, so here are examples of 2 rows of the edges. Very good. Okay, now what is this powerful property of the edge incidence matrix that helps with graph sketching? A very nice property is the following. Well, note, so suppose that I have a graph and I want to approximate the cut structure of this graph. For instance, here's a graph on the slide, and suppose I want to understand how many edges go across a cut S. So I have a set S of a subset S of vertices, and I'm interested in the number of edges that cross the cut, to go from S to minus S. So here on the slide, the cut is to the bottom and to the top of this red line. All right. It is convenient for our purposes to encode a cut through the indicator vector of the cut. So for a cut S, a subset of vertices, let X be the indicator of that subset of nodes. So X is a vector of length n that has a 1 on, for all positions corresponding to vertices in S, and a 0 otherwise. Okay, so this is equivalent to just assigning binary labels to vertices of the graph. Vertices on one side, this is the S side of the cut, get a 1. Vertices on the other side of the cut get a 0. Good. Well, the nice observation that underlies graph sketching primitives is that b times x is the signed indicator vector of the cut delta of S. Indeed, if I pick an edge, say this edge here, that crosses the cut, then b times x is what? B times x, I'm right multiplying the vector b by x. B times x will be a 1 plus a 1 times one of the endpoints, plus 0 times the other endpoint. And if one of the endpoints of the edge is inside the cut and the other is not, then x zeroes out one of the endpoints and keeps the other. So I get a 1 or a minus 1. And if both endpoints of the edge are inside the cut, then the plus 1 and the minus 1 cancel. If both of the endpoints are outside of the cut, well, I'm multiplying by zeros anyway. All right, good. So b times x is a signed indicator of the set of edges in the cut. Now this happens to be a very powerful observation. And in particular, this observation allows us to solve the following interesting problem. Suppose that I receive a sequence of edge updates, sort of insertions or deletions, and at the end of the stream, I'm given some cut S. So I didn't know it before the stream arrived, and what I want is to be able, at the end of the stream, when I'm presented with this cut, to output an approximation to the number of edges that cross the cut. Okay, if I knew the cut in advance, that would be easy, because I would just ignore all the edges that don't cross the cut. But I don't know the cut in advance. So for instance, for this cut, I should be able to output something roughly equal to 2. And for this cut, I should be able to output something about equal to 7. All right. How do I do that? Well, one way of doing this is to look at the edge incidence matrix B of the graph, and as the edges come in, maintain S times B, which is a matrix with a polylogarithmic number of rows and n columns. So it's a small, it's a pretty small matrix. Here it is. Once I receive the cut, I simply decode an AMS sketch of the corresponding cut. So let me show it here. So I have the matrix B, which is n choose 2 by n. And at the end of the day, I'm given a cut S. And I'm asked to output a good approximation to the set of to the number of edges that cross the cut. How would I do this? I would generate an AMS sketch, for instance. Which is a matrix with a polylogarithmic number of rows and choose 2 columns. So S will be like this. And as the edges in the stream are coming in, I will maintain the product, S times B. Okay, so this product, yes?
The S that indicates the subset of the nodes is different from the sketchy matrix, right?
Oh, yes, thank you. Thank you. So let's say, right, let me call this P prime. C. So suppose I'm given a cut C at the end of the stream, and I want to output a good approximation to the number of edges that cross this cut. What I do is generate an AMS sketch S, and then as the edges of the graph come in, I maintain S times B. And that's easy to maintain because an edge update is simply an update to one row of B. So I can maintain this very cheaply. At the end of the day, what I know is that B times the indicator of C is the signed indicator of the set of edges that go across the cut. Maybe this is my cut C, and these are the edges. So B times 1, the indicator of C, is a vector in R n choose 2, where I have minus ones or plus ones on all the edges that cross the cut and zeros everywhere else. On the other hand, so in particular, the L2 squared norm of this vector is nothing but the number of edges that cross the cut. So if I have an AMS sketch of this vector, then I'm able to get a good multiplicative approximation to the L2 squared norm of the vector, which is also known as the number of edges that cross the cut. Okay. On the other hand, I already maintained S times B. This is a matrix with a polylogarithmic number of rows and n columns. So as soon as I'm given this set C, with the cut that I want to estimate, all I need to do is just right multiply my sketch S times B with the indicator of this cut. This gives me the sketch of B times 1C, and I just decode the sketch to produce an approximation to the cut. So this basically relies on the following observation. This relies on the observation that the set of the vectors that are indicators of cuts form a linear subspace of dimension n, and what we're n minus 1, and what we're doing here is sketching the basis vectors for the subspace, and then later we can recombine the sketches of the basis vectors into a sketch for the cut that we want. Yes?
Do we apply S to B first before applying the indicator function?
Great question. Yes, that's exactly what we do. You see, so as the edges arrive in the stream, we don't know what C will be yet. So we will maintain S times B, because we can do it. This is a small object, only polylogarithmic number of rows and n columns. And then once we're given a cut C, we simply add up the corresponding columns of this matrix. And by linearity, we actually have a sketch of B times the indicator of C. Other questions? Yes?
So this sketch approximates cuts. Do you know if it approximates other other circular vectors? So if it's a 0, 1 vector, it approximates the cut.
Oh yes. So this works for any vectors.
Okay.
Yes, I will get. That's the second part. The second part of the talk. Yes. The vectors don't have to be binary. It's just for binary vectors. This has very nice combinatorial interpretation. Good. All right. Very nice. So this already looks quite powerful. And this is the idea introduced by Anguche and McGregor. Let me summarize. So we first designed very simple, nice linear sketching algorithms for basic statistical estimation problems, namely distinct elements and the AMS sketch. What is happening there is that we have a vector x, this is the frequency vector of the stream, and our algorithm maintains the matrix vector product s times x. And this is a vector with a small number of coefficients in small dimension. In graph sketching, what has worked extremely well so far is the idea of sketching the edge incidence matrix B. So here's the matrix B, which is n choose 2 by n, and we hit it on the left with a sketching matrix S with a polylog number of rows and n choose 2 columns. And again, as before, this matrix S is large, but we can generate it using a pseudorandom number generator. So this can be generated in a small amount of space. Good. And so in graph sketching, what we maintain is a matrix, which is n columns, 1 per vertex, and a polylogarithmic number of rows. So think of really just doing standard sketching operations on a per vertex basis. Okay. And so the fact that the edge incidence matrix has this nice plus minus 1, has the plus 1s and minus 1s, leads to powerful cancellations. Okay, nice. So we have a algorithm that lets us approximate any given cut at the end of the stream. And by the way, of course, this algorithm also extends to the question of approximating any polynomial number of cuts. For instance, if at the end of the stream I don't give you one cut, but I give you some poly n number of cuts, well, you can just use the AMS sketch and set the failure probability to be inverse poly n, and the sketch will be simultaneously correct on all the cuts. Okay. Unfortunately, it will not be correct on it will only be correct on that polynomial set of cuts. Unfortunately, it won't be correct on all the cuts simultaneously, because there are too many of them. Okay, so in particular, this doesn't really give us an algorithm for constructing spanning forests. Okay, but here's the algorithm that actually does construct spanning forests in graphs with the dynamic edge updates using linear sketching. This is the algorithm of Anguche and McGregor from SODA 12. Well, first we start with a simple algorithm for constructing spanning forests, also known as Borówko's algorithm. Well, we initialize our forest to the empty set, and we start by initializing our set of connected components to singleton components, all the vertices. And then the process proceeds over a logarithmic number of rounds, and in each round what we do is the following. We look at every connected component in the graph so far, and for every connected component, we look at the corresponding cut that separates that vertices in that component from the rest, and choose one edge. Every component selects one edge from this cut. Very nice. Then we look at this set of edges, recompute the new spanning forests, and proceed. So, for example, maybe in round 1, these two vertices chose each other, these two vertices chose each other, and so the situation was a little bit different for these four. Okay, if this is what happens in round 1, then in round 2 we have 3 connected components, and then every connected component now selects one edge from the corresponding cut, and we have a spanning tree of our graph. Very nice. Good. A moment of contemplation reveals that the basic step in this algorithm is the operation of sampling a non-zero entry in the following vector. At this point here, given a collection of vertices in the original graph, or given a cut, what we need to do is choose one edge from the graph that crosses the cut. Now, specifically, we know that the if we look at the edge incidence matrix B and multiply it on the right by the indicator vector of that particular cut, what we'll get is a vector with plus ones or minus ones on the edges that cross the cut. Very nice. So it would be very nice if we could design a primitive that selects a uniformly random, doesn't really have to be uniformly random, selects an element of the support of B times the indicator of some set of vertices. Good. Well, luckily this has been studied in the literature, and this is known as L0 samplers. So let me define L0 samplers for you, and then we'll get a sketching algorithm for connectivity. So a delta error L0 sampler is the following object. It's a linear sketch, which is also known as a distribution of matrices that maps vectors in dimension n to vectors in some small dimension m. And the sketch comes together with a decoding primitive. This decoding primitive takes vectors in small dimension m. Think of m as polylog, good compression. And the decoder spits out one element of the universe n. This is going to be the non-zero element of the support. Okay, so the sketch together with the decoder is an L0 sampler if for every x in Rn with the integer poly-n bounded entries, the following is true. If we decode the sketch of x, then the distribution of this one element of the universe that we get is close to the uniform distribution on the non-zeros of x in total variation distance. It's delta close. Informally, think of this as follows. This is a randomized algorithm that either samples a uniformly random element of the support of x, or outputs fail, or just some garbage with probability delta. And think of delta as small. So with probability delta, it can just break and not tell you that it broke, or it can break and tell you that it broke. Okay, this has received quite a lot of attention in the literature recently, and we actually know tight bounds for the space complexity of at least L0 samplers. Good. So now, equipped with this notion of L0 samplers, we can actually get a connectivity algorithm for dynamic graph streams. And the connectivity algorithm will do exactly this. Well, we will go through this natural algorithm, Baruch's algorithm, that constructs a spanning forest in a logarithmic number of steps. By the way, the number of steps is logarithmic because the number of connected components goes down by a factor of 2 at least in every step. And we do the following. So at every point in time, we needed this primitive for taking a subset of the vertices and selecting one outgoing edge from the cut. Well, that's exactly what L0 samplers do. How many times will we need to do this? Well, we know that the algorithm will run for order log n steps. So let's prepare sketches. Let's prepare L0 samplers, S1 through St. So T is order log n. That's an upper bound on the number of iterations of this algorithm. And now, as the edges of the graph are coming in, our algorithm will maintain S1 times B, S2 times B through St times B. Independent L0 sampling sketches for the edge incidence matrix. All right, so now, when in iteration T, the algorithm needs to sample an edge from a certain cut, we just run the L0 sampler on the sketched version. So we take the sketch, post-multiply it on the right by the indicator of the vertices in the cut, and run the decoder. Okay, and as long as our decoder succeeds, which we can control by setting this failure probability to be small, this is a connectivity algorithm for dynamic graphs. Okay, very nice. This is quite surprising because note, for instance, that the algorithm is highly adaptive. We don't really know up front which cuts will emerge as intermediate components in the run of this algorithm. The algorithm is adaptive and runs over a logarithmic number of rounds, but the sketch is non-adaptive. Using the fact that cuts form a linear subspace, we sketch the basis vectors, and then we can recombine sketches of these basis vectors to get a sketch for whatever we wanted. Okay, one other interesting question is, why did we need independent sketches for every round of the streaming algorithm? Well, that is because these sketches cannot be used adaptively. if you think about the definition of an L0 sampler, okay, so a very natural improvement to the algorithm before would have been to just sample one sketch S instead of T sketches, and use that very same sketch in every round of the process. That is not guaranteed to work. Why? Because of the definition of L0 samplers. An L0 sampler is an object that for any given input vector with high probability produces the correct result. If we use the sketches adaptively, then the vectors on which we run become correlated with the randomness that the sketch uses, and the correctness properties break. Although it turns out that, in fact, a limited amount of adaptivity is okay when we use L0 samplers, and that's how one can get optimal lower bounds for the space complexity of L0 sampling. Very interestingly, quite recently, Nelson and Yu showed that showed an optimal space lower bound for any spanning forest sketch of the type that we have seen. In particular, for this sketch, if you set the parameters right and use the best known optimal L0 samplers, then the space complexity will be n log cubed n bits, and this turns out to be needed. Okay, good. There are some simple implications of the spanning forest sketch. Let me just list them. One nice and simple implication is that if we don't just want a spanning forest, but suppose I want the following primitive. I have a parameter d, and I want to list all edges in my graph that have connectivity at most d. Okay, well, actually not quite that. I want to find a list of edges that will contain all the edges of connectivity at most d. You can do that in about n times d space. Simply keep d spanning forest sketches, take out one spanning forest, subtract it from the remaining sketches. By linearity, you can do that, and repeat. So that way you sort of adaptively take out d spanning forests from the graph, and the list of edges that you obtain will contain all edges with connectivity. With some work, one can also obtain cut sparsifiers from this primitive. Okay, let me just say a few words about how one would design L0 samplers. In particular, this is in fact a fairly simple construction that follows the techniques that we used in distinct element sketches. Okay, so a delta arrow L0 sampler is this randomized linear sketch with a decoding primitive that essentially, with probability 1 minus delta, spits out a uniformly random element of the support and otherwise breaks. Good. So basically, we want to take a sketch that allows us to scan a stream, and at the end of the day, choose one of the elements of the support uniformly at random and not be biased towards the ones that appeared very often. How do we construct such linear sketches? All right. The main idea is quite simple. Well, first, suppose that our input vector is one sparse. There's exactly one element of the support. And recall that x is the frequency vector of the stream. Well, if that's the case, then we can recover x by sparse recovery. And using just 2 rows of a sketching matrix, I will show these 2 simple rows in a minute. Okay, very nice. So if x is one sparse, then we know how to solve the problem. And in particular, an L0 sampler just needs to output that one element. So that's good. On the other hand, if x is t sparse for some t greater than 1, then here's what we can do. Similarly to the distinct element sketch, we can imagine first choosing a uniformly random subset of the domain. Every element is included with probability 1 over t. But if x was t sparse, then with a non-trivial constant probability, x restricted to a random subset of size about t actually will be 1 sparse. And we can solve the problem there. And if it is 1 sparse, the element that remains is a uniformly random element of the domain. So good things will happen. Good. So I said that if x is 1 sparse, then I can reconstruct x just from dot products with 2 rows of a sketching matrix. So let me tell you how. Well, the 2 rows are one row with just all ones, and the other row with 1, 2, 3, 4, 5 through n. Okay, if x has a single non-zero, then x is just the coordinate vector in some direction I star times a coefficient. So it's not hard to see that I can read off the coefficient from the first dot product, and I can read off the direction from the second dot product. So the index. Good. So if x is not sparse, as I just said, we can imagine rounding its sparsity to the closest power of 2 and choose a uniformly random subset that contains every element with probability 2 to the minus j, at the corresponding rate. And with constant probability, this will be 1 sparse, and we can recover this. There are some small details to be filled in. For example, that we can actually verify that recovery was successful, but let me not dwell on that. Okay, it seems that I don't have time to talk about the lower bounds, but so let me skip this. And good. Just a quick summary. I showed how to design L0 samplers, and besides L0 samplers, some other basic sketching techniques that are meant for simple statistics of large data streams, and showed how these techniques can be applied to the edge incidence matrix of graphs to get non-trivial graph recovery primitives, namely spanning forests with dynamic updates and optimal space. In the next part, I will talk about other methods, namely sort of classical methods for finding L2 heavy elements in data streams, and I will show how these methods can be applied to achieve spectral sketches for graphs. Namely, right now we just recovered spanning forests. I will show how to use L2 based techniques to recover spectral approximations, namely approximations that will get most of the eigenvalues of the Laplacian matrix correctly to within multiplicative factors and generally preserve the quadratic form. Thank you.
Presented the spanning forest algorithm. You're running Boruk's algorithm at the end of the whole sketch.
So say again?
Currently, in the algorithm for computing the spanning tree, you run the Boruk's algorithm at the very end after the sketch is being computed.
Yes.
Is there a way to do that incrementally so that?
Oh, I see. So the question is, can we not run Boruk's at the end, but rather sort of run Boruk's as the graph is coming in?
Yeah, just if I need to change it, I change.
Oh, I see. So that seems tricky because, in a sense, I can construct a spanning forest and then some edges deleted, and now presumably I need to. Oh, I see. So you're saying, can we also get a quick update procedure? That would be nice. I wonder. I suspect that some of these sketching techniques have actually been used in similar settings, but I don't know if a good answer to this. Yeah, that sounds like a good idea. So maybe one can speed up the maintenance of the forest. Yeah, that would be nice. Let me see. Right. Yeah, I don't know. Good.
What would be an application for L1 heavy element recovery in graphs?
L1. That is a good question, but I don't know an answer to it. No, so at the moment we only, right. So in a sense, L2 basically is, I don't know of a good application. At the moment, L2-based techniques give you spectral sparsifiers, which are strictly stronger than cut sparsifiers. So it's not clear if L1 would help you here. It would be nice to find some, but no, I don't. We don't have any of those at the moment.
What if you just want to know the number of connected components? Does that squeeze anything out of this? Or?
If I just want the number of connected components, okay, in dynamic streams, I see. So if I have dynamic edge updates, and I just need a oh, I see. So the leeway would probably be: do you still need 3 logs, or
yeah,
you need at least you do need omega n. You do need so the space complexity would be between omega n and n log cubed.
So fine. Yeah.
You need n log n.
N log n for the number of connected components.
Just to test if it's connected. There's an n log n lower bound, but
Is it n log n? I thought it was just n.
There's an n log n even for insertion.
I think. I think I only know the omega n. But yeah, I see. I'm not aware of an algorithm that does this with smaller space complexity. Sounds like an excellent question, actually.
Isn't that, in the insertion only, that's just like the union find, right?
Oh, but the question is, can you do it with small space? Right.
The union find is like n, like, it's
Yeah.
a second or something.
So there is an omega n lower bound. Right. So you can't do this in sublinear space.
Right.
So that's, yeah. What is your question?
So, I'm saying if you are in insertion only and you just want to know the number of number of components, you just need to run like a union find, right?
Sure. So you would need at least n space for that.
Yeah.
Right. And so the
question need much more than n space.
right. So the question is, sort of Ken's question is, how many bits of space do you need for dynamic graph streams if you just want the number of connected components? And the answer, for all I know, is somewhere between n bits of space and n log cube bits of space. But I don't think we have techniques for doing it better than n log cubed.
Insertion streams, n log n is tight. I mean, there's an n log n lower bound through indexing. So that also applies to
With a log, okay, then maybe I don't know the n log n one. Oh, okay. Right, yeah, sounds good. Any other questions?